everybody. Let's see. People have joined. Okay, we've got 4 here. Would somebody mind just putting a message in the chat just so I can check that you can hear me and see me and see the shared screen? Great, thank you. And can you also see the PowerPoint presentation first slide as well? Great, thank you. So we'll wait a minute or two just to see if anybody else joins. But the purpose of this is really a bit of a reasonably informal rundown of just what happened when I went and visited China for a week. So I was there for about 8 days, and I hadn't been before. I don't know how many of you have been. Maybe you can put in the chat whether you've been there or not. And I'm not sure what I expected from it, but it wasn't what I expected. But it's a bit difficult to say how it was different, I suppose. And it was quite, I went mainly with the guys from Discover, but I was largely going with people I hadn't met before. Some of them I'd spoken to online, but I basically went to China, a country I hadn't been to before, with a bunch of people I hadn't met before, who at least they spoke English. It was basically, for most of the time that I was there, I was up at sort of 6 in the morning and either on a plane or on a train or in a car going to a factory, and then you're at the factory nearly all day and you're eating with the people that you're with and with people from the factory or the managers of the factory for every meal, and then you're back to the hotel at sort of 10 o'clock at night. So it was quite grueling in that you have to be on all the time, and you're sort of, you know, socializing the entire time and not really master of your own destiny, especially for the first half of it. But a bit later on, I got to sort of have a look around a little bit more myself, and I'll go through that as well. What's the time? It's about 4 minutes past. Let's see how many people we got now. Yeah. So yeah, it will be reasonably informal. You're welcome to just ask questions anytime. Let me just check that this little slideshow thing is working. Okay, I will have to. The rice wine. I didn't have rice wine, but I did have Mao Tai, I think it's called. And so Mao Tai is 50% alcohol. So that it's pretty strong, and it tastes like a solvent, I thought. But it's still, you know, it's still nice actually, but did have a slight solvent vibe to it. Let's just get back to this. Okay, I think I'm going to struggle to actually monitor the chat. I'll have to just go back in every now and again. So let's just check this is. All right. So start the presentation. Okay, so here we are. This is me in Shanghai airport, actually towards the end of the trip. And this doesn't really give you much of a sense of the scale of it, but it's a big airport. It's an airport and a railway station, and it's pretty big. And you can't see much English in this shot, but actually a lot of the stuff is in English, so it wasn't too hard to actually navigate your way around. This is where I was staying in one of the places I visited, and it was pretty fascinating. This hotel that had been built. I'm not exactly what the story was with it, but it was a very industrial area. So it was a very big sort of that never has any guests. So it was a bit like it was all a bit like The Shining or something. There was probably more staff than there was guests, and had this quite weird artwork as well. But it was very nice. Um, this is the view from the hotel window in that particular place, um, and I'll have some more sort of happy snaps a little bit later on. But this is um, the main thing that I got from this was visiting the factories and seeing how they actually make a lithium battery and how that process works. And I didn't know a huge amount about that before I went along. Um, the the main process I'll sort of outline for you here. You can see on the left hand side, this is a mixer, and this is one of the smaller ones. And this is where they mix what they call the slurry, which is lithium and this is the lithium ferrophosphate slurry. I'm not 100% sure exactly which materials go into that, and that they mix it and sort of heat it to make this slurry, which they then, once they've made that material, they then put it onto these copper sheets. So this picture on the left here is a diagram that was on the wall, presumably for visitors like me, to explain the process. And then you can see one of them on the right hand side here. So they make the slurry, and then they attach it to these sheets, almost like a roll of sellotape or something. And then you can see in this picture on the left hand side, there's a top sheet, sorry, a top black layer and a bottom black layer, and then there's a separator in between, and the separator is where the electrolyte is going to go, and that's your anode and your cathode. So they make these long rolls, one with the slurry on it, and the other, which is going to be the other plate, which is, depending on what the material is, can be carbon or whatever they're using, graphite, and then they make them both into the sort of tape, and then they have a separator in between the two of them, and then they get that and they roll it up. So they presumably they could not roll it, and they could just have like a long flat battery, I suppose. But they put them together like a sandwich, and they roll them up, and then they put it in the outside casing. And then once they've done that, they then inject the electrolyte in between those layers. And then they do a forming charge on it. So it's sort of relatively simple conceptually, for how this is done, but it's done with a lot of precision, which I'll show you as we go along. But that's the general process. This is a mixer in this one was at, I think this is at Great Power. It might not be though. So the factory that I went to quite a few, but one of the main ones I went to was a place called Great Power, and their factory was absolutely massive. You have to drive from one end to the other. You're not going to walk from one end of the factory to the other end. And one of the things that really struck me with all of these places, even where they're doing the sort of manual assembly of the batteries rather than making the cells, is how few people are there and how amazingly clean it is. It's all automated, and it's all very precise and very clean, especially when they're making the cells. So you'll see all of these videos and photos I've got in this section. You can see my reflection because I'm on the other side of a window. So this is one of the smaller mixers where they're mixing the slurry. This is actually a little video. I don't think there's much to see there. And then this is where they are this. Let's turn this on. And this is part of how they're applying this onto the copper sheets there. You can see the sheets coming out, and it goes into that chamber there, which is how they bake it on to the sheets. It wasn't 100% clear to me exactly how that process worked, because a lot of the explanations were in Mandarin, and I had a translator, but there's only so much they can translate. And you can see again here on the left hand side, you can see sheets that have the slurry baked onto them. There's 3 of them. You see those 2 blue rectangles in the middle there. You can see those 3 rolls of copper sheets with the slurry baked onto it. And then on the right hand side, you can also see those rolls of them as well. So they bake them onto these big rolls. Now, any of these videos, yeah, that one's a video, and both videos. So you can see you can't really see it moving that well, but they're rolling out, going into a machine where they're then going to be cut and folded, which is the next stage. I didn't get a good photo of the next stage, but then what they've done from here is that they've then put the 2 layers together, and then they've rolled them up into a pack like this. And so these are the packs that have been rolled up by the previous machine. And again, there's very few people involved. There's just people monitoring the equipment. They're not really manually handling the stuff to make these things, because it needs to be really clean and really precise. And it's incredibly sophisticated equipment. You can see in this one here, this is where they are injecting the electrolyte into it. So they've put the 2 plates together, they've rolled them up into that material, and then they are then injecting them with the electrolyte. And before I go on and talk about the automated warehouse, what I didn't get a good ability to take photos of, but what was really interesting is it's quite a long process for how they put the electrolyte in. They inject the electrolyte and they measure the weight of it to make sure it is exactly the amount that they want. And it was done slightly differently at different factories, but once they've done that, they then do a forming charge on it, and let it settle, and then they inject electrolyte into it again, and they measure it with a lot of precision to make sure that there's no bubbles, and that the process has gone exactly how they want it to. Once they've done that, some of them then do another forming charge, because before that it sort of doesn't have any capacity, and that forms it. It's a little, the way they explained it to me was a little bit like when you magnetize a piece of iron or something by stroking it with another magnet or an electromagnet, and that makes all of the makes everything line up, and become magnetic by aligning all the forces. So that was how they explained what the forming charge does. And then once they've done that, they then do a whole series of tests on these cells in order to test the capacity and the voltage of them. And the quality standards are incredibly high. You'll hear people talk about A, B, C, and D grade cells. In the same way, you'll hear people talk about that with solar panels, and I'm not sure how it works with solar panels, but with the lithium batteries, what I thought was really interesting, and I had to ask quite a lot of questions to sort of get through to this, was that once they've made the cells and done all their thorough testing, discharge testing, open circuit voltage testing, and a few others that I didn't quite understand, and that almost takes longer than actually making them. So it's really rigorous. They then grade them by capacity. So these ones that we're looking at here, they were 314 amp hour cells. And these cells are, if they are below 314 amp hours, they throw them out. That's considered to be a fail. And then if it's sort of 314 to 317 in capacity, then that would be a D grade cell. And then 317 to 320 would be C, and 320 to 323 is going to be B, and above that is going to be an A. So that's how they decide whether it's an A, B, C, or D grade cell. And that's just a natural part of the variation of the materials. It's not really that there's something bad about the D versus the A. They just sort of come out with that kind of range of capacity, and then they put them in groups. But what I thought was really interesting was that, and I could see where they put them on the pallets and given them the grading, and they'd charge them to different voltages because different customers ask for them to be shipped at different voltages. They then pass that information about the grade of the cells onto the marketing department, but that description is not passed on with them as about the capacity. They just get sold as 314 amp hour cells, A, B, C, or D grade, but it doesn't sort of get described as what that was, as far as I could tell. And so it's then sort of a lot of marketing stuff about A and B and C, D grade quality and things like that. And it sounds like the way I would have thought about it would be that there was something sort of inherently inferior about the D versus the A, but actually it's just that they're bigger capacity, but there's no other measure of quality associated with that, which I thought was really interesting. Not only that they graded it that way, but also that they didn't, that the marketing department and the salespeople don't really understand that because they're not technical like the guys on the floor are. And the testing is so rigorous, and they're so incredibly careful that the likelihood of having a bad cell is just incredibly low because they'd spend so much time testing them. They're not just sort of putting them together like you might see in a factory and doing a quick test and they all go out the door. They spend nearly as much time testing them and forming them as they do manufacturing them. And I did ask the guys, the chemists on the floor, what constitutes, if a cell fails after it leaves the factory, what would be the cause of that? And he basically said overcharging or undercharging or over discharge, mainly over discharge, is the thing that kills them, rather than being some other manufacturing fault that they then find out about later. So, of course he could just be telling me that, but these weren't marketing people. These were the chemists on the factory floor. So I'm inclined to believe what he said about that, which I thought was really interesting. So it's the cell failures that you might have out in the field are either sort of end user error or perhaps BMS errors rather than failures of the cells themselves. At least if you're talking about the caliber of cells that I went to visit the factories for, there might be others that don't test it as much. The warehouse, so there was a massive warehouse that had this assembly line in it, and this was just one of many sort of identical assembly lines. Then there's a warehouse next to it, which is where they keep all the raw materials. And this warehouse, you don't get much of a feel from it from this video here, but it was basically completely dark because there's nobody working in there. It's just 100% automated and robotic. So when they need more materials, they're called on for more materials, and the pallet gets lifted up by a robot. It gets picked off the shelf and taken by the robot and sent over the road. These are this wasn't actually part of this process. This was later on, but these are some autonomous forklifts which I saw in operation, which I thought were pretty fascinating. I nearly got run over by that because I went over this little pink line when I wasn't supposed to, because I wasn't paying attention. And here's another one here as well. It's just absolutely amazing. And so once the cell is made, it then goes to another part of production, which is where they are actually physically taking this cell and making it into a battery pack, which is a completely different process, really. So there's the assembly of the manufacturing of the cell, and then they make their own batteries with those, but they also sell them to heaps and heaps of other people who make their own battery packs and put their own BMSs in as well. And once it gets to whoever's manufacturing the battery pack, they then go through a whole range of testing themselves as well to test the quality and put them into groups a second time. So this, you can see this here, this is at the manufacturing plant, and this is them testing the open circuit voltage, and I believe they sort of test the resistance as well with a sine wave. And they do that of each battery before they start assembling them as a way of grading them, even though they, as I explained before, they've already come in graded. I think this will show you the little values that come up. Let's see. Yeah, there we go. So there's a resistance and the voltage there. And there's quite a few little tests like this. I didn't always get an opportunity to film and take pictures. And once they've graded them, they then put them together into groups of 4. This is for the Helios specifically. And there's more in this part of the factory. There's more people than in the cell manufacturing, but still, it's like the work is largely automated. These people are largely supervising for the most part. They're putting them into these little trays by hand, and then they put them onto this little conveyor belt, and along it goes. It's pretty cool. And then it goes into this little area here, and this is just to check that the terminals are clean before they weld to them. So they check them ultrasonically, I think. We clean them and inspect them ultrasonically before they then weld them together. So let's see what my video is like for that. Yep, not a lot happening in that. And then once they go in, they then go on to the next little machine, and in they go, and they weld these little tabs on, which have been placed just in a slightly earlier process. After they've been inspected, they put the tabs on, and then they weld them like this. And so because this is just fully automated, the chances of it going wrong are just so much lower. There's a stage after this that I didn't get a chance to photo where they then test the welds as well to check that they're good. And then once they've assembled this little pack of 4 and it's welded together, they're then lifting them into the battery carcass, as you can see here, and you can see it's starting to look like a Helios battery. And they're not, it's being put in gently. They're not actually having to lift them up themselves. They're using this crane operation, so it's not getting bumped around or anything like that. And then after that, they're then installing all the BMS cell balancing circuitry. So this is done a little bit more by hand, but in the Deye factory, they showed me people doing a job like this, and they have there's a counter which counts which measures the amount of torque that they put on, and if they don't do it correctly, there's a little alarm on a TV screen above their head, and it sort of goes to their supervisor. And if that happens 3 times, then the supervisor comes along and they get in trouble or something like that. But I asked him, how often does that happen in practice? And he says, well, it doesn't really happen at all, because the machines are set up to do it properly, and everybody knows to do it properly. But yeah, I thought it was quite interesting that he at least mentioned that was their procedure. They then do a bunch more testing on each individual unit again. That's the BMS. Checking the BMS is reading all the values. And then once they've assembled it and put the BMS in, and it's essentially close to a functioning Helios battery, they then do some quite dramatic discharge tests. So you can see here that all of these batteries are hooked up to massive cables, a big nest of them, and then they go through the wall, and they're monitoring them, and they do a full charge and discharge test, at least one, or I think they did more than one, to check the capacity and check the functionality of the battery. And those cables go through the wall into the second room here. And when I went in there, I was expecting it to be very hot, but it's not, because they're not resistive loads. They're not just throwing the power away. They're actually inverters putting the power back into the building for running the factory, which I thought was great. So that's a bunch of them there ready for testing. I'll just check if there's any messages in the chat. No. And that was the bulk of how the Helioses were manufactured. I also went to the R&D facility, and all of these plants have the main manufacturing area, and then they all have these R&D areas where they're getting batteries in and testing them. They have sort of mini production lines and labs where they're making batteries with different chemistries and things like that. So I thought that was really interesting, because lots of people say, oh, well, all the cells come out of the same factory and they're all the same. But I think, whilst obviously lots of people do get their cells from different places, they can get their own custom formulations, and they are routinely testing out different formulations and developing things. So it's not the case that inside all of them are exactly the same. There's quite a lot of variation, and obviously they're trying to develop their own proprietary formulations to give them an edge over their competitors as well. I'll go on to the high voltage section after this, but I'll just flip back to the main window to see if there's any messages. Fire suppression. So the fire suppression, can you see it in that window? Let's have a look. You can't see it there. Let's go to a previous one. The fire suppression is located, I've got a good picture in my CAD actually of it. So you can see that the legs are at the bottom here, and then you've got the 4 cell packs, and then above that is a gap. On the back wall is where the BMS is, and then just above where the packs end, that's where there's 2 fire suppression little packs, the little square pieces, and they sit above either of those 2 columns, I suppose. And as far as I know, the Helios is one of the few that have them in there. I didn't see any in the other ones that were being manufactured, only the Discover ones, I think. The high voltage ones have them as well, but they're sort of built into the cabinet rather than into the battery pack like these are. One second. Okay. And so the high voltage batteries, these are made with the same cells that the Helios are. So part of the reason that the Helios batteries are so affordable is because they are a large format 314 amp hour cell that are mainly manufactured for these sort of CNI batteries, like these ones that we see here. So these are the ones that are used in like Discover's 210 HV batteries, which I've been doing some work on this morning, actually. We've got 4 of them that we're just about to send out. Yeah, exactly the same cell from exactly the same place. And they come in these massive sort of, I guess you could call it rack mount batteries, and then they get stacked up inside the enclosure like this. So this one's got 1, 2, 3, 4, 5, 6, 7, 8 of them. The ones that we've just got going out the door have 4 in them, and that's about 650 volts. After that, it gets tricky with the inverters for the market that we're looking at, and they're obviously they get very, very heavy. But so you can order them in these different configurations, and this is all manufactured at the same place that makes the cells. And you can see on the right hand side here, the cells are all wired in series, and then they come through to the left hand side here. The top part of it, you can see that's Brendan from Discover on the left hand side. At the top part of it is where the cooling system is, and then the bottom is sort of the battery management area. You've got the large DC isolator on the left, and then you've got the sort of management system power controls on there as well. And you can see that in more detail here. You can see that's the cooling system with the 2 black pipes at the top, and you can see the refrigerant where you can put the extra refrigerant in is that little silver nozzle towards the bottom. This is just more close-ups of all the electronics and how you attach to them. They're surprisingly simple, these big batteries, actually. It really is just those massive black cell packs, and then they get wired in series, and there's a cooling system, and then it goes through to a BMS, which is behind this plate here, which is making sure everything's happy, and it won't turn it on if it's not happy, and it won't turn it on if it doesn't have proper comms with the inverter. And then the contactor clicks in, and it's pretty much all there is to it, really. It has a bunch of safety features that it won't operate with the door open and things like that. And so that was sort of the first section of my trip. Let's check for any messages. Do they need to be removed if replacement of the BMS is required? No, they don't. They're sort of a bit further down. You've got the BMSs on the back wall of the Helios, and then they're underneath that. So you could lift that out. It's the same. It's very similar to the rack mount BMS, but actually probably more serviceable. On the rack mount, you take the entire front panel off, which is pretty good. You take that off, and that's got the BMS on there, and you just take the plugs out and you put another one on. The Helios, you take the front plate off, and then the BMS is mounted on the back wall, and so you just take that PCB out and put another one in. I haven't had to do that. I've done it on a few of the rack mounts. The Helios, they all use automotive grade connectors as well, so they're warranted to go in vehicles, whereas the rack mount aren't, which I didn't know actually until I visited the R&D facility. So that was sort of that section of the journey. That was sort of around Shenzhen and Shuzo. I then caught a bullet train to, let me make sure I get this right. Then caught a bullet train to Kuzo, which is where it was very kindly organized for me by Shirley from Aeson. And that's where the sodium batteries are made. So I didn't get great photos, but the bullet train was really fascinating just to sit and stare out the window and actually have some downtime for once. And it was incredibly smooth, even though it was going very fast. It was really smooth, and nice big luxurious seats and things. Yeah, so I went up to Kuzo and saw the Aeson factory. So Aeson do sodium batteries, and so for those of you who don't know, sodium is not like the old saltwater batteries that were popular sort of for a very brief period of time, sort of 6 or 7 years ago. Sodium batteries are sodium ferrophosphate batteries, and so because sodium is just above lithium on the periodic table, it has the same valence value that that lithium does. It basically, you could say, it's the same jigsaw shape atom as lithium, so you can use it in a very similar way. It's just less reactive because it has a higher atomic weight. The valence electron is further away from the nucleus, so that's kind of like two magnets being further away. So it's a less reactive version of the same type of atom, you could say, which makes sodium batteries safer, but they slip into the, but they're lower energy density, but they slip into the same manufacturing process very easily. The benefit to them is that sodium is so much more abundant than lithium, and that they don't have the thermal runaway issues because they're less reactive. And the other aspect to them is that you can discharge them all the way down. So what that means is that when you have a lithium battery, you have two plates, and the lithium, you've got a bunch of lithium ferrophosphate compounds, and they all have a set voltage differential between them and the other plate. As you discharge it and take lithium ions away from that, you're sort of breaking those compounds down. And the ones that remain, the lithium ferrophosphates remain, is still 3.5, but the average voltage, it's a bit like pulse width modulation, goes down as you're taking those lithium ions off that plate and putting them on the other plate. But you can only take so many of those off before that plate, which is made of lithium ferrophosphate, disintegrates or is damaged. So it's like you can only take a certain amount of them. Say there's 100 lithium ferrophosphate compounds. Maybe you can only take 20 of them before you're going to damage the integrity of it. So there would be potentially more power there, but you can't take any of that if you want to have a functioning battery. Sodium, because it's a bigger atom, is just it's more resistant to that. So the plate has more integrity, and so when they take those atoms, the sodium ions from that plate, they can take pretty much nearly all of them, and so you can effectively discharge it much lower. So the energy density is actually nowhere near lithium, but because you can use almost 100% of it, it then gets it to a similar ballpark. But that means that the voltage window is massive. So lithium has a really small voltage window, a bit like a lead acid battery, because you're only using kind of a fraction of it. And that's the same as a lead acid battery. You all know that you can actually discharge a lead acid battery all the way down to 2 volts, and it will function all the way down, but it might not ever charge back up again. You can leave your car battery lights on overnight and kill a new battery just once if you're unlucky. So the sodium battery allows you to use that entire range, but it means that your charge range is, instead of being from 48 to 55, for instance, it's going to be from 20 to 45. It's a massive range. So that restricts some of the applications for it. But anywhere where you've got power conversion equipment, that doesn't matter, especially with the high voltage inverters. They already have huge voltage windows because they're expecting stacked series batteries and different amounts of them. So they make them with these massive voltage windows. So it doesn't matter for those at all. So it's quite an exciting bit of technology, which is just sort of becoming available on the market now. Some of you would have seen Aeson at All Energy, and the litmus test, I think, for this type of stuff was a few of them, but you hear a lot about new technologies, you read about it online. But the litmus test is, can you buy it and use it, I think. And so now sodium is at a point where you can buy and use it, because you can buy through us Aeson sodium batteries. This is a rack mount 48 volt one that you can see here. I didn't get to see them manufacturing the rack mount one when I went there. You can see here, this is at Aeson, this is them making automotive batteries. So you can see they've got the individual cells that they're putting together in packs here. And again, the same high standards of production that I was talking about before. But these are going into automotive batteries, starting batteries. And I thought that was really fascinating, because despite the voltage thing I was telling you about, because they have the other advantage is that they're much better in cold climates. They can go down much lower and be charged at a much lower voltage than a lithium battery can be. Lithium batteries really don't want to be charged much. If you're below 5 degrees, you can't really charge them. You can discharge them, but you can't really charge them. Whereas the sodium batteries go down much, much lower. I forget the value off the top of my head, but it's sort of negative 15 or something. And so they're very popular in markets for replacement car batteries where it's very cold. So in parts of Eastern Europe, I think. I've actually got one of these for my car. I haven't actually put it in yet, but I've got one I'm going to be putting in as my starting battery in my car. And it should last a really, really long time. And it's not, I'd be maybe, lithium ferrophosphate is pretty safe, really, but I'd be maybe a little worried about having a lithium ferrophosphate cranking battery in my engine bay, because it gets so hot. But for sodium, it's just not an issue. They also are working on a high voltage sodium battery. So you can see in the middle here, that's an absolutely massive sodium cell that they've got, and then they're stacking them up. You can see it on the left hand side here, and it's a very similar format to the high voltage batteries I was just showing you from Discover, and then they're putting it into a large rack mount case in a very similar format. It's not available yet. They reckon maybe they were putting this together for TUV testing when I was there. They reckon sort of 4 months, and then it will be commercially available. But I think that will be a very interesting space for C&I, especially with some applications where they don't let you put lithium batteries in at the moment. Yeah, here we go. That's the high voltage cell on the right hand side, and that's the cabinet on the left. So how are we going for time? Daniel, trains in China put us to shame. Yes. Yeah, they do put us to shame, and just the ability to do long-term planning puts us to shame as well. Oh, Chris, negative 30 to 80 degrees Celsius operating temperature. There you go. So much better than lithium ferrophosphate. After this, I then went to Shanghai, which is fascinating. It's like 28 million people or something like that. And I then, the next day, I caught another bullet train to Ningbo from Shanghai. That wasn't quite as nice as the one from Quizhou. It was still pretty good, but it wasn't sort of quite as relaxing as the one from Quizhou to Shuzo. And I went to the Deye factory. I won't show you pictures from there because they all look very similar to the ones I've already shown you. But that was fascinating as well. They manufacture the batteries and the inverters there. And I got to have a sit down with one of their main engineers and really sort of get into some really sort of technical conversations. And it was really good to go and just make the connection so that I now have them. The Chinese equivalent of WhatsApp is called WeChat, and I've got a WeChat account, and I now have a bunch of engineers from all of these places, but from Deye on my WeChat, and so I can talk to them about any issues I've got. So straight to the manufacturers, which is really good. And it was really fascinating. The factory there, they all, not everybody, but a lot of them live at the factory. So there's a big apartment complex sort of next to the factory, and they're all very young. They're all about sort of 25. You know, I think there's upsides and downsides to that, but they don't have the commute is very good. But it's all, you know, it's all very work focused, but not. Everybody seemed to be very enthusiastic and enjoy what they were doing, I thought, as well. So it was an interesting situation. And they were making some pretty impressive large format batteries at the Deye factory as well. And again, the facility is absolutely enormous and largely automated for most of the time. And interestingly, at Deye, a lot of more stuff was done in house compared to some of the other places, like making the steel fabrication of the enclosures and things. They did that in house, whereas most of the other places, if they did do that, I didn't see it. I think they mainly got that in from other fabricators for that stuff, and they concentrated on the assembly and the cell manufacturing themselves. Not sure if they make their own cells though. Can't remember on that one because I didn't get to see that part of the process there. And so we're very close to the end. So that covered about 6 days of visiting all of these factories and basically being sort of up at the crack of dawn and you know, with visiting factories and talking to people and having lunch and dinner with them every day till about 10 o'clock at night every day for about 6 days. And then on the last day before I went home, I managed to have a day myself around Shanghai. I managed to rent a bike because everything over here puts our public transport system and everything else to shame. They just have an app with a QR code for the public transport system. And so once you've got, I was using Alipay, and you pay with Alipay, you don't use your credit card or cash. You've basically got this one app that you use for public transport and for paying everything, and you can use it for hiring these bikes, like kind of a bit like Lime bikes, and all sorts of other services as well, all sort of done through this one app. But it took me a while to get that to work. And riding a bike through Shanghai was the traffic rules are pretty different, but in a funny way, it really works because it's much looser on red and green lights, but everybody is driving really defensively and not really driving very fast. So you don't have this thing that we have here when somebody might, if it's a green light, people just go through the intersection, not expecting anything to happen. And if something did, you probably wouldn't be able to do anything about it. Whereas in Shanghai, everybody's always expecting something to happen. And so everybody's driving defensively. And so in some way, it's actually kind of safe. I wouldn't say it's safer, but it has its own system that seems to work quite well. So I was able to ride a bike around, and it was a really good way to see Shanghai. And I was able to sort of go places that would have been too far to walk, or wouldn't have bothered had I not had the bike. And then in the evening, I went to, let me just switch over back to that PowerPoint. In the evening, I went to this place called the Peace Hotel, which is up in the Bund. The Bund is on the river and is an old sort of heritage listed area that was when the British were in China. And it's all these old, sort of looks like old London town or something, all these beautiful old sort of Victorian style buildings along the river. And they call it Shanghai Noir. And this band is playing at this old hotel called the Peace Hotel. And these guys, you don't have a good feel for it in this picture, but the average age the guys playing in this band was about 75. And there's an article about it, a newspaper article on the wall that talked about that. The oldest member was like 84 or even older, I think. And they've been doing it with very few changes for about 30 years. And it was really great music. This is an area of the Bund, a bit like Times Square. I've got the video, but I think actually there wasn't going to be any sound because of the way that it's not, because of the way that I converted it to put into PowerPoint. But if you're keen, just send me an email and I'll send it to you. This guy was great player, great saxophone player, and this woman had a great voice as well. And I was sitting next to a couple who I struck up conversation with, and they were the guy was an artist. I hadn't heard of him, but he was a reasonably sort of famous artist, and had just had an exhibition opening in Shanghai, so he was quite fascinating to talk to. And yeah, so that was a really nice way to sort of finish the trip. And that's pretty much the end of it. But the main takeaways for me was just seeing what a high level of quality everything is, especially the cell manufacturing. That it's very precise, and there's huge amounts of time spent on the checking of the cells. So it's very unlikely to get sort of faulty cells, which I hadn't really appreciated that before I went there. And just seeing that, anything you want to get made can be made, because there's just that industry is all together in a tightly packed area, and they're all sort of, they work for this place and they go and work for this other place, and they all sort of know each other and talk to each other, and yeah, it's really, really very interesting. Does anybody have any more questions? I'll probably go back for the Solar Expo, which is next year in Shanghai as well, and see what new products are coming along. Second time going somewhere you're a bit more comfortable and it's a bit easier. And yeah, if you want any of these slides or anything like that, just send us an email. Did you ask them if they could put a 2-pole breaker? Yes, I asked them. I ask them pretty much every day if they will do that. Yeah, it's a sore point for me, because it's a pain that it doesn't have it. But it's because of the American market that it hasn't got it. And the reason is not because they can't put it in, it's because it costs an absolute fortune to have the stuff tested, and so they have to have it tested again if they changed it. So that's the reason that they haven't done it. I don't know why they didn't do it to begin with. I guess they just but I haven't got a slide for this, but the other thing I spent quite a bit of time with the guys at Discover working out is a set-top box and a combiner box for the Helios. So one is a box that will sit on top of the Helios and has the breaker built into it, and it will have pre-made cables pre-attached that go down and attached to the Helios, and then it will have Amphenol connectors on the top of the box that you then run up to the inverter. So you don't have to sort of wire into it and get in there and put your cables in. You just slot it on top, click with the two Amphenol's on the battery, and then you'll have another pre-made Amphenol cable, which you'll connect with Amphenol's to that, and then up to your inverter. That's for one. Helios and one inverter. And then if you're going to have multiples, what I worked on with them for design, and I'm just getting costing and stuff at the moment, is an enclosure that will have multiple breakers in it, and they'll be joined with a bus bar, and it will have Amphenol connectors on the bottom. So you just place that on the wall, and then you install your Helios, and then you're just going to run pre-made Amphenol connectors from the Helios to this box, and that will be your 2-pole breaker. And then it will have another 2 breakers which will come out of that, which can go to your inverter. So there'll probably be 125 amps, which is going to give you a reasonably sized inverter. Let's just do our maths. So, you know, a 5 kilowatt inverter, for instance, and you could have an MPPT. And if you needed a larger inverter, then you could use the 2 125s, 2-pole breakers and the Amphenol connectors coming out, because the larger inverters all have 2 studs in them anyway. So you run 2 positives and 2 negatives out to your larger inverter. What I'm working out at the moment is whether you might need to replace those 2 125s with a single 4-pole, which is the same as two 125s, but it's joined to be one circuit breaker. And that would make installation really, really quick. So you can have 3 batteries going in and a small MPPT, well, a medium-sized MPPT and a small inverter out of the other 2, or you can have a large inverter with 2 cables. Yeah, so I'm getting costing and stuff on that coming through at the moment. Be sometime early next year, hopefully. Yeah, it should be a good thing. And the set-top box is pretty much done, and that will be coming up very soon. That'll make installation of a single Helios really quick. Just putting the finishing touches on that at the moment. So yeah, we're pretty much out of time. Any other questions before I close it off? Stop sharing here. No. Okay. Well, thanks everybody for coming. And we'll probably be doing another 1 or 2 maybe before the end of the year. And otherwise, have a great Christmas and see you next year.